The last property of an antenna that I wanted to discuss is called antenna effective area or antenna capture area. And it tells us how much radiation is collected by an antenna. So when an electromagnetic wave is propagating in free space, it's got some sort of plane wave propagating in free space here, it's got a power density associated with it. And if I put some sort of antenna in its path, the antenna is going to convert this power density of the EM radiation incident into the antenna into a voltage and current that flows in the transmission line that connects the antenna to the load. So the antenna is converting the power density here into a power delivered to an electric load. And it does that, since power density is in watts per meter squared, it does that due to its antenna area, A sub E right here. So to describe the amount of power that this antenna can capture when an EM wave impinges or travels across it, we use this antenna effective area or the antenna aperture, which is, it's defined as the ratio of available power at the terminals of the receiving antenna to the power flux density of a plane wave incident to the antenna with the wave polarization match. So we're not considering any sort of polarization mismatches. So what does this mean? Well, we've got PT, it's the power delivered to the terminals of the antenna, and that's going to be equal to whatever the power density function is times the capture area of the antenna. And the interesting thing about this is capture area of an antenna is not a physical area. It's just related to the ability of an antenna to convert power density into actual power. Sorry, I've got that backwards. It's PT divided by power density. It's the ability to deliver the power density of free space into some usable power at the input terminals of the antenna. So it is not actually equal to some physical measurement of the antenna. So then, how then do we calculate it? Well, we could measure power at the terminals of the antenna if we knew the power density of the wave, but that's typically not what is done. Instead, we've got a formula for antenna capture area, and we relate it to gain. And that's going to be the antenna capture area is equal to the wavelength of the electromagnetic wave squared. We divide that by 4 pi, and we simply multiply it by gain. And typically by this we mean gain max, the max gain. So for example, let's say we have a 5 gigahertz signal, so F equals 5 gigahertz, and let's say that the gain of the antenna is 15 decibels related to an isotropic emitter. What's the capture area? So the first thing we need to know is calculate lambda. So lambda is just, since this is a wave in free space, it's C divided by the frequency, which is 3 times 10 to the 8th, divided by 5 gigahertz, 5e to the 9th. So that gives me a free space wavelength for the signal of 6 centimeters. Gain was specified in dBi, so I've got to undo that, and so I can find actual gain. That's equal to 10, 15 divided by 10. Hopefully you understand where that came from. If not, you can come talk to me. This gives me 31.623. Now I can calculate capture area of the antenna, which is just 6e to the minus 2 squared over 4 pi times 31.623, and that gives me a antenna capture area for this particular antenna of 9.059 times 10 to the minus 3 meters squared. So what effective area does is it just simply represents how much power is captured from a plane wave by an antenna and delivered to the receiving circuit. This area factors in losses intrinsic to the antenna, and very, very often we'll use effective or capture area as a method to calculate power transferred from one antenna into another antenna.